Okay, so today what we're going to be talking about is digital circuit components. Okay, now digital circuit components are basically integrated circuits, but these integrated circuits contain things called flip-flops, counters, or shift registers. Okay, now integrated circuits are basically little boxes with silver legs, kind of look like spiders a little bit. And they're made to save space and facilitate the building and troubleshooting of digital circuits. And they use logic gates to actually operate the controls for your circuits. These logic gates are packed into one IC chip. These IC chips are going to be classified according to their packaging and the family that they belong to. Now, the packaging is basically referring to what they look like. What type of package do they come into? Are they in a square, a rectangular shape, or a circular shape? And as far as the family they belong to, it's really referring to the chemistry. Okay, now when you're talking about IC chips, we need to first off make sure that we understand how the pin numbers are set up. So we got to make sure that we're holding the IC chip in the correct direction. If you take a look at these pictures, you'll see that these IC chips, they all have this little notch, okay, or there's a band, or there's a little dot there. We want to make sure that make sure that it's held horizontally, and make sure that that's on the left-hand side. Okay, once you hold that horizontally in the correct position, you'll see that the numbering starts at the bottom and it goes from left to right, just like you would write a sentence, write a word, and so on. So it's going to go 1, 2, 3, 4. Now these numbers are going to increase in a counterclockwise direction. So we're going to start here at 1, 2, 3, 4. When you run out of room here, it goes back up to the top, 5, 6, 7, 8. Over here on this chip, we're starting at 1, going over to 7, and in a counterclockwise fashion going up to number 14. And on this chip, we're starting at 1, going to 8, and then going up to the top, and then going in the counterclockwise section or fashion to number 16. Okay, now when we're talking about the families, we're mainly referring to 3 types of families: TTL, CMOS, and linear. Now, there's some information about these here. The TTL, in the TTL family, the transistor is the basic component that makes up that IC chip, and you usually operate with about 5 volts. The linear family is going to contain mainly analog devices, amplifiers, oscillators, and regulators, and they're going to operate at many different voltages. And then there's the CMOS chips, which basically have field transistors are the major components. Okay. Now, just going back, you can see that the naming conventions are also a little different. The naming conventions for the TTL is not specified, but here you can see that the linear has an LM in the front or a CA in the front. If you take a look at the naming convention for the CMOS, it's basically just a 4 or 5 digit number starting with 40 or 45. When we're talking about IC chips, we've got to be very careful with how they're handled. So we've got to make sure that we try not to touch the pins. These pins are very fragile. They can be bent very easily, which make it very difficult to insert those into a circuit board or insert those into a printed circuit board so they can be soldered. So make sure that you discharge yourself by touching a ground or metallic surface before you touch the IC chip, because they are sensitive to static electricity. You never insert or remove the IC into or from a circuit with the power on. You always got to make sure that the power is turned off or the battery is disconnected. Okay? Don't touch the body or pins of the IC when the power is on. Again, that static electricity could damage the component. And before you connect it to a circuit, make sure the IC is installed in the correct position. If you have reverse voltage in the IC chip, or you have it disconnected improperly, that could damage the IC chip itself. Now, as far as with IC chips, some special notes about them: they cannot be repaired. They have to be replaced. So if something happens with the IC chip and you know that it's damaged, you basically just have to remove it and throw it out. Damaged ICs get hot. That's the easiest way to check to make sure that they are okay. If it is hot, It's probably damaged, so you probably should take it out, let it cool off, try again, and if it still gets hot, then it's damaged. You need to remove it, get rid of it. And now we're going to be moving on to talk about flip-flops. Flip-flops are the basic building blocks of digital circuits, digital logic circuits. These things are going to be wired together to form counter, shift registers, and various memory devices. Basically, the flip-flops are going to store one bit of data. It's going to be a 1 or a 0, and it has two stable states, the 1 or a 0. And it's basically going to be flipping back and forth between the 1 and the 0, hence that's the name flip-flop, just turning it back and on between the 1 and the 0. Now here, this slide is just going over the different types of flip-flops, and we're going to go over some detailed information for these just very quickly. The RS flip-flop is 2 inputs, 2 outputs. It's asynchronous. The RS stands for reset and set. The clocked flip-flop is very similar, but there's an input labeled the clock, okay? And these are always, outputs are always opposite or complementary. This one is synchronous, so that means it operates in step with the clock. The RS flip-flop is asynchronous, but the clocked one is synchronous. The other two families here, D flip-flop, okay, has one data input and clock. It's synchronous, and the D stands for delay, okay? The JK is basically just another one that talks about the different types of inputs here. J and K are data inputs, so this one has 2 inputs, okay, and it's very used, it's commonly used in different things for counters. Okay, now this slide is talking about IC latches. The IC latch is a digital device that serves as a temporary buffer memory, and all of these are in different IC forms. Now, when we're talking about triggering or operating the flip-flops, the synchronous flip-flops are going to operate in step with the clock. The asynchronous are not. It's common to show the trigger symbol on the flip-flop symbol with a small triangle. And if you have a negative edge trigger, you're going to put a circle with the triangle. Now, when we're talking about flip-flops, we also need to talk about something called Schmitt triggers. This is used to shape the signal from an analog shape to a square shape. So if you remember, the analog shape kind of looks like a sine wave, and then we're going to change this to a digital shape, which is basically a square wave, okay? The analog signal has a very slow rise time, whereas the square has a very fast rise time because it's going straight up. The analog takes a little bit of time to get to the input up, but if we want to change it so it comes on very quickly, we're going to use the Schmitt trigger, okay? Another name for this type of manipulation is called signal conditioning. Okay, another type of digital component besides the flip-flop is a counter. A counter is an example of a sequential circuit. Flip-flops are going to be wired together to form counters. So flip-flops are independent, but when they're wired together, they can form counters. Counters can also be made in an IC form, and almost any complex digital system contains several counters. Okay, this slide is just reviewing some functions of counters. Obvious functions, counting events. How many times does something tick? How many times does something move? You can also count time, and you can put events into sequence. Some not so obvious functions that are very useful for counters are dividing frequencies. So if you need to slow something down or speed something up, you can apply addresses or memory units as well. And when we're talking about counters, something very important that we need to mention is something called the modulus, okay? Now, a modulus is basically the number of different states the counter's got to go through to complete its cycle. So if you think about it, counting in binary, if we go through from 0, 0, 0, 0 to 1, 1, 1, 1 in binary, we need a device that has 16 different output states. So that makes that a mod 16 counter. And on the next slide, I'm going to count through these just to show you. You can see the sequencing of a mod 16 counter, starting at 0, 0, 0, and then going up and just increasing in one step each one. You can see at the bottom of this first row, it goes to 0, 1, 1, 1. And then when we flip over to this other side, it picks up with the next sequence and then goes all the way up to the 1, 1, 1, 1. And that is the mod 16 counter sequence. You should be prepared to be able to count in binary from 0, 0, 0, 0 to 1, 1, 1, 1, or be able to sequence that. if it's all jumbled up. Now, another type of digital component that you can look at is something called a counter. Okay, and these are some examples of counters: ripple counters, mod 10, synchronous, down counters, self-stopping, IC, and frequency dividers. And the next few slides are going to go through some examples or some information about these. Okay, the ripple is basically just a chain reaction that ripples through the counter. The mod 10 ripple counter is something that goes from 0, 0, 0, 0 to 1, 0, 0, 1. The synchronous counter is used for high frequency applications. The down counters are used if you need to count backwards. Okay, and then there's the self-stopping counter. The down counter recirculates. It starts over and does not stop. And the IC counters are customized. You can have many different combinations for those. Now you can use counters as frequency dividers. So here's an example of how that's this is how it's explained to do. So if I want to take an input frequency from a power line and I have to reduce it. Now when I'm looking at frequencies, I have to think about hertz. A hertz is a cycle per second, so you should know what these units are. If I need to take a circuit and divide it by a frequency of 60 in order to get the frequency of 1 cycle per second hertz, how can I do this? What you can do is you can take a decade counter, it's going to divide it by 10, and wire it in series with a mod 6 counter, and then the 6 times 10 will give you 60, okay, and that will give you the frequency that you need. So whatever frequency that you need, you can kind of look at the modulus of the counter, multiply them together when they're in series, and that'll tell you how you can divide the frequencies. Frequency dividers are very useful in timepieces like digital clocks, auto clocks, and wristwatches. They're also very useful when you're counting frequencies, when you're using oscilloscopes, and when you're doing TV servicing. Now, the last digital component that we're going to talk about is something called a shift register. Shift register is where we're going to take multiple inputs, funnel the data to a single output, or single input transfer to multiple outputs. I can take one or more inputs and funnel that to one or more outputs. So it's made of flip-flops and latches. Okay, here's an example of how a shift register works. You can think about a calculator. If you type in the number 268, type in a 2, type in a 6, and then the 2 basically shifts it to the left, then the 6 takes its place. Then there's you type in the 8, the other two numbers are shifted, and then the 8 is there, and then the calculator reads 268. So these are formed by wiring different flip-flops together. The key thing that you need to know about shift registers is they have two important characteristics: memory. They hold the numbers on the display even when the keyboard number is released, and that's temporary, so the memory exists. And then there's the shifting, where it takes the numbers or the data and shifts it to the left when you press in the new digit on the keyboard. Okay, now here's a pictorial example of the shift register types, and you can look at the serial input, serial out, serial in, parallel out, parallel in, parallel out, or parallel in, serial out. And you can kind of see, if you take a look at those pictures close up in the PowerPoint, you can see it makes a lot more sense, where you can take the multiple single or multiple inputs and then funnel that to single or multiple outputs. Okay, and these last couple slides are just going to talk about the different types. So serial load shift registers, basically, it's got a couple of disadvantages. It only permits about one piece of information to be entered at a time, and it loses all the data at the right side when it shifts right. Okay, and if you talk about parallel shift registers, this system permits parallel loading. Okay, so it's a little bit more advantageous there. And then lastly, okay, we have universal shift registers, which are very adaptable. Okay. I hope that's been very educational to you. Please play the video again if you need to review any of the information.